In this video, we'll use some of the material from the previous video to talk about discriminants of polynomials and start to see applications of all of these ideas to computing Galois groups of polynomials of low degree. Okay, so in the last video, we saw this splitting field of the general polynomial whose coefficients were given by these independent indeterminants, S1 up through Sn. And we saw that the Galois group of that extension had the Galois group of that extension was Sn. So what do we know about subgroups of Sn? A lot. One thing we know is for n at least 5, An is the only normal subgroup of Sn. Okay, there's something to prove here. This is like a Math 206A type result. You should think about whether you remember how to do this. The idea is that An is a normal subgroup of Sn. It has index 2, so it's automatically normal. So if you have another normal subgroup of Sn, well, if you have a proper non-trivial normal subgroup, it can't be contained in An because, we know that An is simple for n at least 5. So there are no proper non-trivial normal subgroups of An. So if you have another normal subgroup, you can take its intersection with An, and it's either all of An, in which case the only possibilities are An and Sn, or it's the trivial group. So now you have An, this normal subgroup of index 2, and then some other normal subgroup, and they intersect in the trivial subgroup, and that tells us something interesting about that other normal subgroup, and I'll leave the details to you to think about. Okay, so what does this mean? For n at least 5, there is only one subfield, E, of f adjoin x1 up through xn, containing f adjoin s1 up through Sn, for which E over the base is a Galois extension. So that's because there's only the one normal subgroup. The index of that normal subgroup is 2, so the degree of this Galois extension is also 2. Where does this quadratic extension come from? Okay, now we'll talk about the discriminant. So the discriminant of x1 up through xn is defined to be the product over all pairs I and j. So let's say I is less than j of xi minus xj squared. So for every pair of roots, you take the square of the difference between them. What is the discriminant of a polynomial? The discriminant of a polynomial is the discriminant of its roots. Okay, what is true about the discriminant? It is easy to see that this is a symmetric function in x1 up through xn. So we know that it is an element of the field generated over f by s1 up through Sn. Okay, so this discriminant is going to tell us about this quadratic extension. But in order to see why, let's go all the way back to section 3.5 in Dummett and Foote, when we first talked about the alternating group and the sign of a permutation. So I actually didn't talk about the sign of a permutation in the same way as the textbook here at the beginning, but I did come back and talk about how it's presented in this section. So if we have an element, sigma, in Sn, when is it contained in An? Well, the motivation there was the sign of a permutation. Is it even or is it odd? Is it 1 or is it minus 1? But what did that mean? Sigma in Sn was contained in An if and only if sigma fixes the product square root of d, this product over all pairs I less than j of xi minus xj. Okay, so this is some polynomial in x1 up through xn. Why is it called square root of d? Well, we've just taken the squares away from d here. Okay, so what happened, right? So when you apply a permutation sigma, you're still getting a product of a whole bunch of x something minus x something else. And when you make these switches that come from the permutation, you pick up a whole bunch of factors of minus 1. So sigma turns this product into minus 1 to the something times that product. And that power, whether it's minus 1 to the 1 or minus 1 to the 0, determine whether that sigma was even or odd. Okay, so that's what's going on here, is that certainly sigma sends this product to -1 to some power times itself. And the question is whether it's fixes this product or it sends it to its negative. Okay, so by the fundamental theorem of Galois theory now, applied to this extension, if f has characteristic not equal to 2, then this element, square root of d, well, okay, this is fixed by everything in an and not fixed by things not in an. So square root of d generates the fixed field of an, this subgroup of the Galois group. So this subgroup has index 2. It generates a quadratic extension of K, this unique quadratic extension, E over F adjoin S1 up through Sn. So let me just say briefly why this characteristic not equal to 2. Well, in this description where we said something is in an if and only if it fixes this product, sigma sends this product to plus or minus itself. In characteristic 2, 1 and -1 are the same element. So that's not the right description of what's going on to distinguish between Sn and an in this field extensions in characteristic 2. So for the foreseeable future, we're going to avoid characteristic 2 for exactly this reason. When the characteristic is not 2, we can understand this degree 2 Galois extension in terms of square root of d. And in characteristic 2, we have to do something else that I'm not going to talk about here. Okay, so I'll pause and erase, and we'll see what can we do with this. Based on the discussion that we just had, I want to make the following assumption for the rest of this lecture, and probably also for the next one. Let's suppose that F is a field of characteristic not equal to 2. So honestly, a lot of what I'm about to say also works for F being a field of characteristic equal to 2, but I'm going to forget where exactly I want to specify now this characteristic not 2 assumption is important. So it's okay with me if you just, for the purposes of this lecture and the next one, forget about characteristic 2, where things are clearly a little more complicated. Okay, so let's take a polynomial f of x to the n plus n minus 1, x to the n minus 1, plus a1x plus a0 in f bracket x. Let's name the roots of this polynomial. Let's say that it's alpha 1 up through alpha n in a splitting field, not necessarily distinct. The discriminant of this polynomial is d, the product over all I less than j of alpha I minus alpha j squared. When is this 0? This is a product of a bunch of things in a field. So this is 0 if and only if one of these terms is 0. So d equals 0 if and only if f of x is not separable, if the alpha I are not distinct. If there's some term where you have one root minus another root that gives you 0. So those two roots are the same. Okay, so when does that happen? Remember, over a perfect field, every irreducible polynomial, f of x and f bracket x, is separable. So that means that if the roots are not distinct of this polynomial f of x, then d equals 0. We can see that. And we know that f of x is reducible. So the discriminant being 0 or not 0 is discriminating between f being reducible or being irreducible here. This is part of why this is called the discriminant. Okay, so what's true about the discriminant? The discriminant is a symmetric function in the roots of f of x. So if you permute the roots, you get the same function back. If you permute, like say switch alpha 1 and alpha 2, you pick up a minus sign in this product, but because you're squaring it, it cancels out. So what does that mean? If E is the splitting field of f of x over f, we know that any sigma in the Galois group permutes the roots of f of x. This is a symmetric function in the roots. So when you permute the roots, you get back d. So any sigma in the Galois group fixes d. But we know the subfield of E consisting of all of the things that are fixed by every element of the Galois group by the fundamental theorem of Galois theory. The fixed field of the entire Galois group is just f. So that means that the discriminant is in f. So that's not obvious, because these individual roots might not be in F. They might really be in some extension of F. They might be in the splitting field, but not in F. But this combination of the roots lies in F. Okay, so in fact, D is a symmetric function in the roots of f of x. In fact, it's also true that D is a polynomial in the coefficients of f. So that is not obvious. And we're going to see some examples of this for low degree polynomials. But you can think about this more generally. Okay, so the last thing I want to say here is square root of D that we were talking about earlier. This is this product over I less than j of alpha I minus alpha j. So these alphas are all in the splitting field of f of x over f. So square root of D is certainly contained in the splitting field of f of x. So when we talk about the Galois group of polynomials, one thing we want to know, I mean, what are we asking about? We're asking about the Galois group of the splitting field of that polynomial over f. Square root of D is some element contained in the splitting field that is not necessarily in f itself. So we're going to want to understand, what do elements of the Galois group of this splitting field do to this element square root of D? It gives us an interesting element in the splitting field to think about. Okay, so I'll pause and erase, and I'll talk more about this idea. Let's finish this lecture by talking about when the Galois group of a polynomial f is a subgroup of an, and then seeing an example of polynomials of degree 2. Okay, let's say f of x and f bracket x is separable and has degree n. We're going to fix an ordering of the roots of f of x, which allows us to view the Galois group of f, the Galois group of the splitting field of f over f, as a subgroup of Sn. We're going to prove that the Galois group is a subgroup of an if and only if the discriminant D, this element of f, is the square of an element of f. Okay, so this is a place where a characteristic of f not being 2 is important, because we said earlier that the description we gave of when sigma, a permutation in Sn, was actually an an, was when it fixed this element square root of D in f. So originally, the description was sigma is an an if and only if sigma fixes the square root of D, this element in z bracket x1 up through xn. Sigma certainly sends that element to plus or minus 1 times that element. And if the characteristic of f is 2, those are the same thing. So we have to avoid that. But otherwise, sigma fixing that element in z bracket x1 up through xn is the same as sigma fixing that element, not in z, but in f. In any field where 1 and minus 1 are not the same thing, you get the same description. Okay, so what does that mean? The Galois group of f is contained in an if and only if every element of the Galois group fixes square root of D, which is this product over I less than j of alpha I minus alpha j. Okay, so this is what we're saying here. But what does that mean? If every element in the Galois group fixes this square root of D by the fundamental theorem of Galois theory, this square root of D has to be in the fixed field of the whole Galois group, which is just f. So this is equivalent to saying this element, square root of D, is in f. And square root of D being in f, D is some element of f. So that's just saying D is the square of an element in f. Okay, let's finish this lecture with this example. Let's talk about polynomials of degree 2. Remember, the characteristic of f is not 2. So let's say f of x is x squared plus ax plus b, and the roots are alpha and beta. What's the discriminant of f? It's alpha minus beta squared. Alpha squared plus beta squared minus 2 alpha beta. Okay, so this is a polynomial in the elementary symmetric functions in alpha and beta. So S1 is alpha plus beta, S2 is alpha beta. Take S1 squared, and you get alpha squared plus beta squared plus 2 alpha beta. So it's S1 squared minus 4 S2. Okay, but If you now rewrite f of x as x minus alpha times x minus beta, then you can see that a is equal to minus s1 and b is equal to s2. So what is the discriminant d? It's a squared minus 4b. This is the normal, usual discriminant of a quadratic polynomial that you probably learned whenever you talked about the quadratic formula in high school. So what are we seeing? F of x is separable if and only if the discriminant is not 0. If and only if a squared minus 4b is not 0. We know we can identify the Galois group of f as a subgroup of S2. When is it contained in A2? Remember, A2 is the trivial subgroup of S2. When is it contained in A2? Well, if and only if this discriminant is the square of an element in F. If a squared, if and only if a squared minus 4b is a square in F. All right, so we have our quadratic polynomial. We know when it's separable. When it is separable, the Galois group is either going to be S2 or trivial, and we can tell which by looking at this discriminant and whether or not it's a square. Okay, so let me just say, this makes sense. This matches up with our earlier discussion of roots of quadratic polynomials, because we showed that the roots were given by negative a plus or minus the square root of a squared minus 4b over 2. So we get the same root for both plus and minus if and only if the thing under the square root sign is 0. And the roots are in F, which means the splitting field over F is just F itself. If and only if this element square root of a squared minus 4b is in F. So everything that we've said here is consistent with our earlier quadratic formula discussion. So in the next lecture, we'll talk about Galois groups of cubic polynomials and quartic polynomials, and we'll solve a bunch of example problems, including some from algebra qualifying exams.